Intro to Limits, pre-calculus version, which is the same thing as calculus version. Nathan's going to read for us. Go.
All right. The limit is fundamental to the study of calculus. It is important to acquire a good working knowledge of the limit before moving forward, because you will find out through the duration of this course that really it is all about limits.
This calculus course is really testing my limits. All right. So limits is not actually calculus. However, it's tested in calculus. It is part of our pre-calc standards as well. But it's kind of the bridge between all of your math before and calculus. That's kind of what limits are. So it's a fundamental theorem that we need to understand. Let's get going. So I want to use our calculator to generate this graph right here. I want to graph this in our graphing calculator. So we should get a graph that looks like that. Now, if you just look at the graph that the calculator did for us, is there an issue with 2? Is there an issue when x equals 2? According to this graph, does it look like there's an issue? Not really. However, what if we substitute in 2 into this function? 2 squared is what? 4. So then I have 4 minus 4, which is 0. So I get 0 on the numerator. And then what's the denominator going to be? 0. Well, what happened there? So back in the day, we did rational functions like this. What happens when you get a 0 over 0? What does it create? It creates a hole. It creates a hole. So I actually have a hole going on when x is equal to 2. That's really what's happening. Now, we can get a limit though. All right. And we kind of did this, but I want to do it numerically here. So I want to figure out this table. So I want to do second calculate on our graph. So we do second calculate, and then I want to find a value. And I want to find a value at, let's say, 1.9. So if I substitute in second calculate value at 1.9, what do I end up getting? So we end up getting 3.9. Now I want to get a little closer. I want to get a little closer to 2. So now I want to do the value at 1.99. So I'm going to do second calculate value at 1.99. And what do we end up getting? 3.99. And then I want to get even closer. I want to get even closer to 2. So I'm going to do second calculate my value at 1.999. And what do I end up getting? 3.999. All right. Now, if I second calculate at 2, what does it do? It gives me a blank. Because why? Because it's a what? Because it's a hole going on at 2. So now if I go to the right of 2, if I do second calculate value at 2.001, I end up with what? 4.001. And then I think we can figure out the pattern. This is going to be 4.01, and then this is going to be 4.1. All right. So anyway, so when I do a limit, there's a hole going on at 2 though, right? Yeah. But what do we think? If we were to trace it, if we were going to go from both sides, what do we think 2 should be? It should be 4. It should be 4, should it not? All right. If I go from the left, it's really getting close to 4. If I go from the right, it's really getting close to 4, right? So at 2, it looks like it should be 4. However, is the value 4? No, my value doesn't exist, but my limit is actually 4. Okay? So I basically filled in its gap, and that's what a limit does. All right? So let's talk about the definition of a limit here. And Darian's going to read for us.
If the y value of a function f of x becomes close to a single value L as x gets closer and closer to a point C from both the left and the right side, then the limit of function x as x approaches C is L.
All right. Go. Okay, go ahead, keep going.
Which can be written using the mathematical notation as...
All right, so this is how we read it. This is called the limit as x approaches C. That little arrow is x approaches C of our function, and our function is this x squared minus 4 over x minus 2 in this case, is equal to an arbitrary number L. It's equal to a y value, and we're just going to call it L because is it the same y value all the time? No, so we just made it a variable. So this is what I want you to do. I want you to put your hands out. I want you to put your hands out. Remember these days? days? All right. So this is what a limit is. So I'm going to say, what's a limit? And you're going to say it approaches from both sides. It approaches from the left and the right. It approaches from both sides arbitrarily close to a number L. All right? Do you know that you ever had that little brother or little sister says, I'm not touching you. I'm not touching you. You remember that? You ever had somebody do that to you? All right. If not, get a little brother or little sister and have them do it. All right? Rent one. All right? So that's what a limit does. All right? It gets arbitrarily close, but it doesn't have to touch. Is it allowed to touch? Yes. However, does it have to touch? No. All right? So here we go. Let's put them out. Put them out. This is what a limit is. What's a limit? When you approach from both sides, arbitrarily close to a number. Okay? It has to go to the same number. Sound good? All right? So if we use this definition on this problem, the limit as x approaches 2 of this function is equal to what? It's equal to 4. All right? It is equal to 4. Here we go. So let's look at example 2. Let's look at example 2. So I need to find the limit as x approaches 2 of g of x when g is this piecewise function. All right? So it says my piecewise function, I have a value of 1 when x does not equal 2, and then I have a value of 0 when x does equal 2. So let's look at this, how it works graphically. All right? So if x equals 1 when x does not equal 2, well, what is it when x equals negative 4? What's my value? 1, right? How about negative 3? 1. How about negative 2? How about anything except for at 2? It's going to be 1 the whole time, except for at x equals 2. Agreed? And then at x equals 2, what happens? I have a dot at 0. So when x equals 2, it is at 0. All right, the value is at 0. So now, if I have to talk about a limit, if I tell you about a limit as x approaches 2 of g of x, again, what's a limit? Guys, put them out. What's a limit? When you approach from? Both sides. When I approach from both sides, it goes to the same number. So if I approach 2, 2's right here, agreed? Yeah. If I approach from the left and I approach 2 from the right, you see how it's going from both sides? Mm-hmm. What value is it at?
0.
1. The value is 1. So the limit as x approaches 2 from both the left and the right is at 1. Does that make sense? What if I had g of 2? That one is the value of g at 2. What is the value of g at 2, though? 0. But the limit is equal to 1. All right? So I have this bridge example. And Sharkbait is going to read our bridge example.
The last example can be confusing at first, but think of a damaged bridge crossing a canyon. Even though the bridge is broken and it seems like the missing section has fallen into the water below, you can probably tell where the missing section should be. The height of that point would be the value of the limit. Limits are important because they give us the ability to discuss what is going on at a point mathematically, whether the bridge or graph exists at a point or not. With limits, you are only concerned with the y value the graph approaches, not with the y value actually is at that point.
All right, exactly. So a limit's approaching the bridge from both sides. All right, so we're approaching from the left, we're approaching from the right. Where's the bridge, though? It's in the canyon. True? However, where should the bridge be is kind of what a limit does. The bridge should be up here. Does that make sense? All right, that's what a limit is. Okay, so that's the All right, so now we're going to talk about one-sided limits. All right, first, let's make sure we know. Let's everybody raise your left hand. Everybody raise your left hand. Red, good. All right, now everybody raise your right hand. Good. Okay, I think this class has a shot at it. All right, here we go. So when we do a one-sided limit, we approach just from one side. Now, a limit, a pure limit, is approaching what? From both sides. All right? But we can do one-sided limits. So let's look at this statement here down below. So if we have a limit as x approaches c from a little plus sign, this plus sign means from the right. All right, this plus sign means from the right. Does that make sense? It's the positive side of it.
Yeah.
Okay? And then if I approach x approaches c from the left, okay, that has a little negative sign. All right, that little negative sign means the left or the negative side of whatever it is, a little bit less than. Does that make sense? All right, so now let's talk about it. So if I approach C from the right, this is the right of C. Agreed? This is to the right. So I'm approaching this little line from the right. Does this make sense? And where is it approaching? It approaches at L. All right? And then if I approach C from the left, this is to the left of C, yes? And if I approach from the left, it goes down to the value of K. All right? See how that works? I actually kind of want to keep going on this one. I know this is a little further, but what is F of C? Is F of C K or is it L? I know this is later on, but I want to do it now.
Okay.
L. Why is it L? Because it's filled in right there. All right? It's L because it's filled in. Now, for a limit to actually exist, the right and the left-hand limits have to be equal. All right? They must go to the same arbitrary number. All right? The same number. Now, does this limit actually exist at C? No, because when I approach from the left, it's K. When I approach from the right, it's L. All right? So my limits don't actually match up, so my limit doesn't exist. However, a one-sided limit, it sure does. All right? So here we go. Let's graph this. So example 3. I need to graph 5 minus 2x when x is greater than 2 and x minus 3 when x is less than or equal to 2. So where's my problem area at? When x is equal to what? Where might my domain issue be? At x equals 2. So that's what I want to substitute in. So I'm going to substitute in 2 in this top one. What do I get? I get 1. So at 2, I get 1. All right, does everybody agree with this? And is it going to be an open or a closed dot? It's going to be open because x cannot equal 2 there. As x is greater than 2. So now I'm going to use its slope. So now I'm going to start sloping that. What is the slope of that part of the graph? Negative 2. And I'm going to the right. So now I go down 2 over 1, down 2 over 1, and I make my curve, or my line in this case. All right? So that one's that top part. Now let's deal with the bottom part. So again, where's my problem area? At 2. So now if I substitute in 2 in the bottom one, what do I get?
-1.
I get -1. So is that going to be an open or a closed dot? A closed dot at -1. See how we did this? Now, what's my slope on this one? 1. So now I'm going to have a slope of 1 when x is less than 2. So that's the graph of that function. See how we did that? All right, so now let's look at part B. So part B says the limit as x approaches 2 from the what?
Left.
The left. I'm approaching x equals 2 from the left. All right, so this is to the left. Does everybody understand that this is left?
Yeah.
So I'm approaching 2. This is x equals 2, yes?
Yeah.
So I'm approaching this from the blue line, basically. So what's my limit as x approaches 2 from the left? -1. The value would be -1 there. All right, let's keep moving. So now I'm approaching 2 from the what?
Right.
The right. So let's go right of 2, and I'm going to trace this line basically. So what is 2 from the right? +1. All right. So I end up getting +1 here. Now, part D asks for the limit as x approaches 2. Now, again, what's a limit? When you approach from? Both sides. And it has to equal the same number. So this one, what happens? What happens when I approach from the left? We did this already. I get what? Negative 1. When I approach from the right, what happens? I get 1. Are they the samesies? No. So it does not exist. The limit as x approaches 2 does not exist. All right. And Ava's going to tell us why. It's a what? This is a jump discontinuity. All right. Reasons a limit won't exist is when it has a jump discontinuity. I call this a special high five sometimes. However, you can't call it a special high five on the AP exam. I've had people ask. So, guess what happens? You ever try to give somebody a high five and you missed? You missed? All right. A limit exists when you meet together. Okay, that's a limit. Okay, it approaches the same number. It got there. You follow me? However, a special high five, what happens? It missed. Did it go to the same number? Did it go to the same y value? No, that's a jump discontinuity. That's what it's called. All right, it approaches two different numbers from the left and the right. You missed. All right, that's a special high five. All right, so here we go. We're going to talk about when limits don't exist. And I need another reader. Thanks so much, Alina.
There are times when a limit fails to exist, meaning that we are unable to find a value for the limit at the given point. When this happens, we say that the limit does not exist, or remain the same in SDN. There are three types of common function behavior that lead a limit that does not exist. F of x approaches a different number from the right side of C than it approaches from the left side.
All right, you can say that's one of the reasons. So you'll say does not exist. It approaches a different number from the right and the left. Or what we can call it is a what? A jump discontinuity. All right, that's a little bit shorter than saying it approaches two different numbers from the left and the right. Okay, you can say that or you can say it's a jump discontinuity. Jump discontinuity is a little shorter. All right, keep going.
F of x increases or decreases without bound as x approaches C.
All right.
And f of x oscillates between two fixed values as x approaches C.
All right, and I want to add a fourth one. At an endpoint. All right, you can't actually take a limit at an endpoint, and we'll talk about why. All right, I've seen many calculus textbooks. I got a lot of them. They never add this fourth one. If I were to write a textbook, they'd have this one on there. All right. You know what? Let's talk about it now. Why can't you have a limit at an endpoint? Why can't you? If I have this endpoint going on right here, why can't I actually get a limit at that endpoint?
Because it's not coming from two sides.
Exactly. This one, I could take a limit as it approaches from the right, but can I actually do it from the left? No, I can't actually approach an endpoint from a left. All right, does that make sense? So I think that there should actually be a fourth. Here we go. So we're going to investigate the existence of this limit using a graph and a table. We're going to do both. Why not? All right, so let's build the table to look at the graph. So if I substitute in, let's say, negative 0.1. If I substitute in negative 0.1, what do we get in the numerator? 0.1, right? What do we get in the denominator? Negative 0.1. So 0.1 over negative 0.1 is really what? Negative 1. All right. How about if I substitute in negative 0.01? What do I still get? I get negative 1. And then I get negative 1. What happens if I substitute in 0? I get a whole. I get does not exist. It's a whole, right? So from the left, I'm going to be negative 1 the entire time until I get to 0. You agree? All right. So now let's go from the right. So let's substitute in 0.1. So what do we get if we substitute in 0.1? 1. How about 0.01? 1. How about 0.001? 1. 0. I still get a whole, right? So my graph to the right of this will be 1 the entire time. So my limit as x approaches 0 of this function, absolute value x over x, what's my limit? Does not exist. Why?
Because they don't agree.
Nope, 0 being a whole is fine. All right, I'm actually cool with that one. Because that's why we do limits, honestly. If we get a whole, we can still take a limit a lot of the times. This one we can't. However, why can't we here? It's one of the 4 reasons.
Different y values?
It's a what? It's a jump discontinuity. All right, this is a jump discontinuity. It approaches 2 different values from the left and the right. Let's write it out more. Let's write it out more. If I have a limit as x approaches 0 from the left of this function, what do I get? If I approach 0 from the left, what do I get? Where does it go? It goes -1. If I approach the limit as x approaches 0 from the right, well, what do I get? I get +1. For a limit to actually exist, you have to do it from what? Both sides. Does my limit exist? Does it go the same number? No. It's a jump discontinuity. It's my special high five. Does that make sense? All right, let's keep. Here we go. Example 5. So we're going to investigate this existence of this limit going on. So I want to actually graph this one. I want you to graph it. So let's fill out our table. So we're going to do second calculate, and I'm going to put in value of 0.9. So what is my y value when I get 0.9? 100. I get 100 there. Now I'm going to do second calculate value at 0.99. We're going to get closer. What do I get? 10,000. All right. What if I do 0.999? I'm going to guess you add 2 more zeros.
Yeah.
All right. So guess what I get? 1 million. I get 1 million. All right. Now, what happens when I put in 1? What happens? Doesn't exist. All right. Now, we'll talk about why that doesn't exist in a second. So then, if I substitute in 1.001, I end up getting 1 million again.
1 million.
And then if I substitute in 1.01, I end up getting 10,000. And then if I substitute in 1.1, I end up getting 100, right? So at x equals 1, what's happening? It's getting really, really fast going up like that, right? It's going super high, super high. True? See it? All right. So what happens when I substitute in 1 right here? What happens? I get a number over what? 0. What happens when you get a number over 0? A vertical asymptote. So I actually have a vertical asymptote going on here. So does my limit actually go to a value, a y value? No, it doesn't exist. And this is going to say because it increases without bound. Because the closer and closer we get to x equals 1, guess what? It's going to get bigger and bigger. They're going to keep going up. Okay? Can you even get closer to 1 than 0.999? Sure you can. All right? Add another number on it. All right? And it's going to keep going and getting bigger and bigger. That means it's increasing without bounds. What if they went down? Then it would be what? Decreasing without bounds. Sometimes they do a little jig like this. Sometimes they have like a little asymptote going on and you go like whoop, whoop. Okay? That one would be a what? Increasing and decreasing without bound. Does that make sense? All right. So that's another way a limit does not exist. All right. I'd like you to graph this one in your calculator because we're going to do some values real quick. Just kidding. Don't put it in your calculator. We got this with our unit circle because we got the unit circle in our head. Yes, 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 yeah, we do. All right. So if I substitute in 2 over pi, well, it's on the denominator, so we flip it, right? So this is really sine of pi over 2. All right, so what's the sine of pi over 2? 1. Awesome. And then if I substitute in 2 over 3 pi, I'm getting closer and closer to 0. All right, because 2 over 3 pi is a lot less than 2 over pi because the denominator is bigger. So if I substitute in that, I get sine of 3 pi over 2. What's sine of 3 pi over 2? Negative 1. If I substitute in 2 over 5 pi, that's closer to 0, I end up getting what? 1. And then I get, then I get 1. So what's happening here? As I get closer and closer to 0, what's happening? It's oscillating. It doesn't exist because it oscillates. All right. Does anybody watch Modern Family? I know it's not a show anymore. It's over. It's kind of a sad day. Does anybody ever watch it? No? No? Well, there's Gloria on there. When she talks about a helicopter, she goes, taka, taka, taka. All right? So anyway, that's what I think of when I think of oscillating. I think of taka, taka, taka. All right? It goes back and forth between two fixed values. That's what oscillating means. All right? It goes taka, taka, taka. All right? Pretty good? All right. So we're going to finding limits from graphs. All right? I need another reader. Thank you so much, Junior.
Finding limits from graphs. Hopefully we're getting comfortable with this new idea of a limit value and how it is different from a function value. When trying to find limits and function values from graphs, refer to the following visual aids. When looking for a limit value at x equals c, imagine that you have got a thick vertical line covering up x equals c with only the graph showing on either side of x equals c. You are now looking to see what y value the graph is approaching on either side of x equals c. If the graphs appear to be approaching the same y value, the limit exists and is that y value.
All right, fantastic. So sometimes I have students that get bothered by if it's a limit or a value. All right, a limit is where things are going, where things should be, okay? Where the bridge should be even though the bridge fell apart. That's what a limit is. So if we look at this graph, I'm doing a limit as x approaches 2 here. So if I say I'm trying to find a limit as x approaches 2 of this function, whatever this function is, a limit is when it approaches from what? Both sides. So when I approach from both sides, what value does it look like it's going to? It's going to 4. So my limit exists at 4. Does that make sense? All right, let's keep going. Let's read the other part.
When looking for a function value at x equals c, imagine that you have got shutters on either side of x equals c with only a vertical sliver at x equals c visible between them. You are now looking for the dot or the piece of graph that exists in that narrow sliver. If it exists, the y value of the dot is the function value f of c.
All right. Oh, go ahead, sorry.
Otherwise, the function value is undefined.
All right, fantastic. So if I'm actually looking for a value, I care about where it's at. Do I care about where it's going? No, I care about where the bridge fell into the canyon. All right, I want to know where the bridge is. Okay, where to go. All right, that's what I'm looking for. So now, if I say I want to find f of 2, well, what would f of 2 be in this case? 1. All right, so my limit is where we're going. My value is where it's at. Does that make sense?
Would the limit be 4?
Correct. My limit
It's
is
the
4.
it's the
All right.
same.
My limit as x approaches 2 is 4. All right. Good? All right. So let's look at this and kind of put it all together. All right, so let's look at A. So the first one says the limit as x approaches 0. Well, it's a limit, so that's approaching from what? Both sides. It's approaching from both sides. So here's 0, yes? Here's 0. So if I'm approaching from both sides, I'm tracking from the left, I'm tracking from the right, where does it look like it's going? It's 6. So my limit as x approaches 0 is 6. All right? All right, let's look at part B. So on part B, it says what? 6 approaches from the left. All right, so that's what it's doing. So 6 is right here, yes? If I approach from the left, where is it going? 4. My y value is 4. So my limit as x approaches 6 from the left is 4. All right, let's keep going. So let's look at C. So then I have a limit as x approaches 2 from the what? The left. Well, 2 from the left is over her. So where does it approach to? It goes to 0. All right, so 2 from the left is 0. All right. Now let's look at this next one. A limit as x approaches -6. Well, -6 is over yonder. What is it? Does not exist. This is does not exist. Why? It's an endpoint. Okay? Because what's a limit, guys? When you do what? When you approach from? Both sides. What can I not approach this one from? I can't approach it from the left. Now, if it said limit as x approaches -6 from a little plus sign, a little right sign, then it would be what? Then it would be 0. All right? All right, let's look at this next one. Limit as x approaches 1. All right? Is this a limit or a value? It's a limit. It literally says limit as x approaches 1. So, I'm looking to see where it should be. All right? So, I'm approaching 1. 1's right here, yes? So, I'm approaching it from the left and the right. So, I end up with my limit to be 3. Now, what does f ask us for? That actually asks us for the value. So now I want to know where it's at. So where is this thing at? It's at 1. All right, it's at 1 right there. All right. All right, the next one. What is g asking? Where it's at. I'm looking where it's at. So where is my value at 2? 2. All right, it right up there. All right, that's where it's filled in. All right, let's look at h. So this one asks us for a what? A limit. So a limit is when you do what? Approaching from both sides. So what's happening at 2? Does not exist. Why? It's a jump discontinuity. All right, it's a jump discontinuity. It approaches 2 different numbers from the left and the right. You can either write that or you can just say jump discontinuity. All right, I'm actually cool with just jump disc if you want. All right, good?
Yeah.
All right.